All right, so let's take a look at Unit 4, Lesson 3, Understanding Rational Inputs. So we're going to look at exponential functions where the input values are not whole numbers. All right, so for number 1, we're going to select all the solutions to x times x equals 5 and be prepared to explain your reasoning. All right, so x times x equals 5. So you could say, all right, well, that means that x squared is equal to 5. So then we're going to take the square root of both sides. Remember that anytime you take the square root, you have to add plus or minus. So we've got B is an answer. And then also remember that, okay, none of these are negative. So square root of 5 is the same thing as 5. And then remember that the power is 1, so that's the top part of the fraction, and the root was 2, so that's the bottom part of the fraction. So D is also the same thing. All right, let's take a look at number 2. Select all the solutions to P times P times P equals 10. So that's the same thing as P cubed equals 10, so we could take the cube root. So P is equal to the cube root of 10. And again, that means that our power is 1 and our root is 3. So we've got the cube root of 10, which is E. We've got 10 to the 1/3, which is A. All right. 3.2, Florida in the 1800s. In 1840, the population of Florida was about 54,500. Between 1840 and 1860, the population grew exponentially, increasing by about 60% each decade. Find the population of Florida in 1850 and in 1860 according to this model. All right, so let's take a look at that first. So it was increasing by 60% each decade. So we're going to take our 54,500 and we're going to multiply by 1.6 because it's growing by 60% each decade. And so from 1840 to 1850, it's going to grow by 60%. And let's get our calculator back here. There we go. And so let's make that a little smaller. All right, so we have 54,500, and we're going to multiply by 1.6 because it's growing by 60%. So in 1850, there should have been 87,200 people. And then we can take that answer, enter. And then we can take that answer and multiply by 1.6 again because it's going to grow by 60%. So this is for 1850, and then for 1860, we have 87,200 times 1.6, which gives us 139,520 people. All right. So in part 2, the population is a function f of the number of decades. So we're going to have f of d after 1840. Write an equation for f. So f of d equals, and then what was our starting amount? It was 54,500, right? That's our starting amount. And we are increasing by 60%. So we're multiplying by 1.6, and that's going to be to the power of d. All right, so explain what f of 0.5 means. So remember that that is in place of d, and d is the number of decades. So that means that 0.5 is, well, actually, let's go with f of that because that's what it's asking. So f of 0.5 is the population half a decade, or 5 years, after 1840. So basically, what is the population in 1845? Is really what that's saying. All right, so now we're going to graph our function. So we are actually going to get rid of, oh, that's not what I meant to do. We're going to get rid of that calculator, and we're going to bring up our graphing calculator. That'll be a little bit easier to look at the graph if we have a graphing calculator. All right, so we're going to graph this function. So instead of f of d, I'm going to put y equals, we have 54,500 times 1.6, and that's to the power, oh, that's not squared, that's to a power, not to the power of x. So we're going to put x in the place of d. All right, so then I want to change my window here. So I tap on the gear, and I am going to change my x-axis. I'm going to start it at, we'll go with -1, and we'll go up to 2, we'll go to 3, 3 decades. And then our y-axis, we are starting at 54,500, so we'll do the population in thousands. Actually, no, we won't. We'll do 50,000. We'll go for 50,000. And then we'll go up to maybe like 200,000. Okay. And then you can see here, and then we can kind of modify that if we want to. But you can see where it starts at 54,500 and at 0 time. And then at 2 decades after, which is right in there, that was your 139,520. Okay, so there's what the graph can look like. And, you know, your axes are going to change the shape of the graph a little bit. If we had changed the decades, let's do that. Let's change the decades to just up to 2 and see how that changes. So notice that that made our graph look a little bit wider and not quite so tall. All right, so explain why we can find the value of f of 0.5 by multiplying 54,500 by the square root of 1.6. Okay, well, remember that if f of 0.5 is 54,500, and then we're multiplying by 1.6, and that's raised to the power of 0.5, well, that's the same thing as 1/2, right? So that's 1.6 to the 1/2, and remember that the 2 is the root and the 1 is the power, so that's the same thing as the square root of 1.6. And then for part 4, what is the population of Florida in 1858? And so that would be 1.8 decades after 1840, so that'd be f of 1.8. So let's plug that in. So that's 1.8, and we can actually just plug it in here. So 54, actually, I'm gonna do y equals 54,500 times 1.6, and then we're gonna raise that to the power of 1.8. And you can see right there, they intersect right there, and so that is 127,003 approximately. And actually, since we're talking about population, I'm going to make it 2 because you can't round a person up. So we'll go with 2. All right, so that's how you can use graphing to help you with solving populations. All right, let's take a look at disappearing medicine. All right, so the amount of medicine in the bloodstream of a patient decreases roughly exponentially. Here's a graph representing F, an exponential function that models the medicine in the body of a patient T hours after the injection is given. So they start off with 12 milligrams at time 0, and after 1 hour, they have 3/4 of the medication. Oh, no, they have 3/4 of a milligram left. So it's depleting fairly quickly. All right, so let's look at our new graph. So we have y equals, and we're starting off with 12 milligrams. And how much is it depleting after an hour? Well, oh wait, they already gave us a graph. Okay, there we go. So we don't even need this one. Let's take a look at this. All right, so 1/3 would be about, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1, 2, 3, 4, so it's about right there. So that's fairly close to 5, maybe about 4.7 milligrams. There are about 4.7 milligrams of medicine in the body. 1/3 of an hour, or 20 minutes, after injection. All right, after 1 hour, 0.75 milligrams, or 3/4 of a milligram of medicine remains in the bloodstream. Find an equation that defines F. So we know that F of t, it's a function of time, equals 12 was our starting amount, and we need to figure out how much it's decreasing by. So what is, and we'll just do it on this calculator, what is 12 divided by 0.075? No, that's not what I want to do. All right, so 0.75, 75 divided by 12 gives us 0.0625. So that is our multiplier. That is our constant multiplier. And then we're going to raise that to the power of t.